Welcome to Section 1.5, Introduction. Make sure to read pages 63 to 72, which include the Chapter 1 summary, and complete Exploration 1.5. This intro is a bit longer, so be prepared to take some notes. In Section 1.5, we will start talking about theory-based methods for hypothesis testing about a single proportion. Not long ago, we did not have the computer technology to create all of these simulations easily. It could take hours, if not days, for a computer to simulate 1,000 repetitions of 457 coin flips. And since people didn't want to wait around that long, or sit around flipping coins or spinning spinners all day, they used mathematical theory to come up with an alternative method of analysis. Theoretical approaches to hypothesis testing are still considered the norm, and many introductory statistics classes at colleges throughout the nation never even cover simulation, though many statisticians would argue simulation methods are better, so consider yourselves lucky. When we use simulation-based methods, we all got slightly different p-values because of the randomness of the simulation. The more repetitions we would do, the closer our p-values would be to each other. We can alleviate that concern with these theoretical approaches. In theory-based methods, we will use a theoretical distribution to model our null distribution, and therefore we'll all get the same p-value. First, we need to understand a bit of the theory used here before we blindly use it. Perhaps you have noticed that all of the null distributions you have created so far have the same shape, roughly symmetric and bell-shaped, with no extreme outliers. The central limit theorem, or CLT for short, is sometimes called the fundamental theorem of statistics because so much can be done as a result of this theorem, and it explains why the distributions are all shaped the same. The CLT states that, under certain conditions, called validity conditions, the sampling distribution of p hat is distributed approximately normal, centered at pi with standard deviation square root pi 1 minus pi over n. What does all that technical jargon mean? Say we take a sample of 40 students from the MSU student population and plot the proportion of women in the sample. Say that proportion is 0.4. Let's plot that on the number line. Our friend decided to do the same thing, finds the proportion of women in a different sample of 40 students from MSU. The second sample proportion is 0.48. Plot that on your number line. Now, let's say each student in your class got a sample of 40 students. Then we plot the proportion from each of those samples of 40 students. The plot we are creating is called the sampling distribution. It is a plot of the statistic, the proportion, from many, many different samples of the same size, in our case, size 40, taken from the same population, in our case, MSU students. The central limit theorem tells us a few things about this plot. First, it tells us that it will be approximately the shape of a normal distribution, meaning it will be bell-shaped and symmetric. Secondly, it tells us it will be centered at the true value of the parameter, pi. According to MSU, in 2016, 46% of the student body was female, so the distribution will be centered at 0.46. Third, it tells us that the standard deviation of the sample proportions can be approximated using the formula square root pi 1 minus pi over n. In this case, the square root of 0.46 times 1 minus 0.46 divided by 40 is 0.0788, or on average, each sample proportion of females among 40 MSU students will be roughly 0.788 away from the true proportion of females at MSU, 0.46. That means, even with the one single sample we usually take, we know that if we took many samples, the distribution would be normal, with mean pi, and we know that its standard deviation will be found through the square root of pi times 1 minus pi divided by n. And that's all well and good. But what if MSU had not published the population proportion of females? What if we don't know the value of pi, as is often the case in real life? Based methods in our tests of significance, because we always assume we know the null hypothesis is true, and in the null hypothesis, we are saying we know the value of pi. So wherever pi shows up, we can use the null value pi naught in place of it. Instead of comparing an observed statistic to some simulated null distribution, we can compare the standardized statistic to what we call the standard normal distribution to obtain a p-value. The standard normal distribution is just a normal distribution, something bell-shaped and symmetric, which is centered at 0 and with standard deviation 1. By standardizing our statistic, we are comparing our statistic to that standard normal distribution scale. In fact, we don't even need to do a simulation to find the standard deviation of the sample proportion like we did in section 1.3, because now we know the formula to calculate it. Hypothesis testing can now be done with only a calculator. Technically, we still need a little technology in order to find the p-value, though a TI-83 would have that technology, and actually there are tables out there to help you find those. But the applets will find the p-values for you, so let's just use them. Theory-based methods are often considered a shortcut. Just a couple of punches into your calculator and you're all done. But they don't hold for every data set the way simulation methods do. The central limit theorem requires a large enough sample in order for the shape to be approximately normal. How large is large enough? In the case of one proportion, we want at least 10 successes and 10 failures. That means, in the example of MSU students, we would need at least 10 women, success, and at least 10 men, failures, in our sample in order to trust the results from a theory-based method.